Happy Halloween. Go ahead. It's due Sunday night, I believe. When did I give you the assignment? Monday. It's due next Sunday. You have a week from when I give it to you to when to do it.
It's the Sunday that's right after the today.
Today's Wednesday. Here, let's give you an actual date. So this is a bad thing. Yeah, November 4th. Tomorrow's the 1st, 2nd, 3rd, 4th. Yeah. Speak to me.
I think it's in everyone's interest to make it Wednesday. I don't know.
Okay.
I assumed it was Wednesday.
I see. Yeah, I didn't. All right, I will. We can do that. It's possible I may give you another assignment on Monday that would be due on Sunday, but I would say it very clearly if that were the case, okay, so that you were all aware of it. Or maybe we'll just go back to Wednesday, due Tuesday night, okay? All right, thank you for asking that.
Wait, so is this one due Tuesday night then, or still Sunday?
Yeah, here, I will update it so it's due to here. Actually, I could do it as we speak, right? Oh, wrong owner. All right, so it's going to say it's due. I'll even put it Tuesday, November 6th. Okay? Winston, there was something on Monday that I asked you to remind me of to say in class. Do you remember what it was? Something about, was it the project? Yes.
Oh,
thank you. It was very useful. Appreciate that. So, no, it worked. So the thing about the projects was the rules for working together are not as strict as they are when you're doing basically the pair work on your assignments. So you need not be physically together, one keyboard, one mouse as you're working together. You can split up work. You're still all jointly and separately liable for it, you know, for understanding it, but you don't have to be working like that, okay? And so that provides a little more flexibility in terms of, you know, not necessarily having to find a time to get together to work on it all. Okay, so today we're going to talk about sequence model architecture. So we learned about what an RNN is. As we look at backpropagation through time, we'll just remind ourselves a little bit. So we're going to go through the different models that we looked at, one to many, many to one, many to many, many to same. But we're going to now look and say, okay, let's say we have that. How do we actually organize our recurrent neural network in order to do that? Then we're going to look at backpropagation through time, which is a cool name, which is really just backpropagation. You just sort of unroll it, you do backpropagation, it all just works. But this sounds a lot nicer. So, and we're going to look at how this passing the gradient from hidden state to hidden state back through time works. And then finally, we're going to look at bidirectional RNNs. So what we'll have looked at so far is RNNs moving in just one direction. We're going to look at actually moving in two directions. Any questions? So let's say we've got a many-to-one architecture like this. So we've got a movie review, and we want to find out whether this is a positive or negative review. So the way we would organize this is something like the following. We'd have hidden states, and I'm showing this unrolled. And then we'd feed in words here. Actually, would we feed in words? We'd fit in probably one hot encodings into a dictionary, but I'm going to just show it as a word here. But actually, I'll just remark it's really one hot encoding from a dictionary. Same thing's going to be true for all the rest. So then we have of, we have a. Do we have outputs coming out now? So I would say we can look at it sort of as either yes or no. We could actually design it so there's no outputs coming in now, or we could have outputs coming in now that we don't care about and we never look at. And they're not part of our loss, and so we don't care what it's doing. So we can kind of think of sort of shadow outputs if we want, or we don't have to. Does that make sense? Okay. And then we keep going, and eventually we get to scene briefly. And at that point, we have an output. And this output is of what type? What activation function? Yeah, sigmoid. Okay, and so this is our y hat. Officially, it's also sort of our y hat or our y hat at time step t. I'm going to make capital T mean the last time step. So this is at capital T, which is the length of our review. You had a question, Drew? That answered it? Okay. Good. And we're calling that our y hat because we don't care about the rest, right, if they were there. Does this one make sense? Okay, so that's how that one would work. And in order to do this, what we probably want to do is have a pre-trained network that's already got a language model. So we fed it a bunch of Wikipedia, let's say, right? Tens of thousands, hundreds of thousands of articles, so it's got lots and lots and lots of English text, so that its RNN really understands English text well. We would use that dictionary and then feed in a movie review. And we might have a little so we might have, like, let's say, 2 fully connected layers here, which would start out with random weights, right, just pre-initialized weights. And we'd be learning then from these features that are coming from the state, right? Because this state consists of some number of features, that is, some number of neurons, right, that represent some information about this review and what we've learned so far, right, by the time we get to it. And so then we'd have some 1 or 2 fully connected layers that can then go ahead and do some processing of that and come up with our sigmoid. Does that make sense? So the rest of it would start out trained. We would basically just be training this. Once we train this, maybe we do a little fine-tuning of the rest of it. All right, that's pretty straightforward. Let's try this one. So we've got a picture, and we want a caption. Of course, for all this, we've got to have label data in order to do the training. So we're just assuming that. So here's what we would do here. We would take this picture, and we would feed it into a CNN. All right? And that CNN would then have, at the last layer, some outputs. Right, we've some activations. In the past, what we've done is taken off the very end of something like ResNet 34 and added in our own connected layer to go ahead and learn dogs and things like that. Here, we would do that same thing. We would chop off the very last end of it and take those activations and now feed those in as our initial X and really our one and only X. Okay, so this is going to be our single input to our RNN. It goes into the hidden state, We go through time with more hidden states. Do we feed in more input? No, it already got it all. So what are we going to do? Yeah, we need to be outputting. So we need to be outputting. This is y hat at 0. And y hat is the, right? If y, I said 0, and that doesn't match with x1, so let's make this a 1. So this is y hat 1. Y at 1 is the, right? So basically it'd be a one-hot encoding into our dictionary with the. What do we have here? What kind of output are we using here? What kind of activation function? Yeah, we got a sigmoid. Sorry, you said softmax. I somehow said sigmoid. So it's a softmax. How many softmax neurons are there? Number of words in the dictionary. Exactly. That's going to be true for every one of these y's. I shouldn't have drawn so many circles. Okay, so we've got basically we'd want the probability of the to be high. And we're training it so that the probability of man is high, right, as we go along. And here we want the probability of on to be high. And so if we've trained this perfectly, it's going to be spitting out high probabilities for the, man, at, bat, readies, blah, 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 all the way to high. No, all the way to on. But we got a bit of a problem here. In a previous example, let's say in here, we know how long to run this. We've got our input, which is this text, and we keep going until we get to the end of the text. And then we look at the output. What about here? How do we know when to stop? We could somehow tell it. Summarize this in 10 words. You know, do it in a haiku with 17 syllables. So that'd be one possibility. And then we just stop at 10. It's another possibility.
Different words have like a different probability of ending the sentence.
It could be that, so we could have an on in the middle here and an on at the end. In fact, theoretically, we shouldn't be ending an on, right? Because that's ending in a preposition, but we are. So, yeah.
Maybe have some kind of threshold for the softmax probabilities and kind of, if you reach a certain threshold, like if you're below the threshold, then maybe just stop.
So if we have, let me see if I'm understanding. So we have a minimum threshold for softmax, and if none of the softmaxes achieve that threshold, we stop. That could work. So basically, I'm not very sure of any word here, is what you'd be saying. The only that would be hard with training, because in training it's going to start that way, right? During training, it very often is going to be I don't know what it is, and so you'd end up for training saying, well, okay, here's one word, actually no words, and I don't know what it is. So that might be great, but it's a possibility. Are you going to say, Abel?
Stop when you have at least like 3 nouns for this.
So there are two parts. There's the neural network deciding when to stop, and there's us deciding when to stop. Are you suggesting the neural net is deciding when to stop, or we're deciding we've seen 3 nouns, we'll stop?
I'm suggesting that like we can train it not like separate from the entire process to recognize how many it needs for something, like how many like parts of speech it needs.
I think it could very well learn that, right? It could look and it could say, there's a CNN here, and I've got enough information for my features to figure out that there's 3 objects in there, or 4, or whatever we think is the right number. And I should really describe all of them, and once I've done that, I'm done. here's what I'm going to suggest. We have another token. We're not done yet. I'm going to just make it period, right? But it could also just be, end, something like that. Something that says, I'm done. Period in this case works because captions are one sentence normally. But in general, we can have just something that says end. So as far as when I'm doing inference, I feed this into the CNN. And by the way, the CNN and the RNN are really the same network. It's one big network. It's not like we're going to have two separate networks necessarily. So we feed this in, we go, and we just keep looking at the output and keep looking at the output until, yeah, probability to end is higher than anything else. End or period, which however we want to talk about it, right? Some special token that says, I'm done. I gave you all the words. Don't ask for any more.
This is probably like dumb, but would there ever be a case when we would have like the possibility for multiple punctuations, like exclamation marks or like question marks?
Oh, sure.
So would we have like sort of like divided across all possible like ends?
Let's make it probability of a special symbol called end. Okay, so we have 30,000 words in our dictionary. 1 through 30,000 are our words. 0 is end. Sometimes you also need a start symbol. And so we might have a few different symbols. We might actually add another symbol, which is unknown word. Well, this is going to be generating unknown words. But when you're recognizing text, sometimes you might need that. Make sense?
So the CNN is pre-trained, right? Not like training that.
There's no particular reason to pre-train it. Or to train it again, yeah. We would use two pre-trained. We would use a CNN that's pre-trained. We'd use a RNN that also already has a language model for English that's pre-trained. And then we'd go ahead and make this better, yeah.
How do we know that we want a specific probability of like on or like at?
For on, so we know that our y, right, our ground truth, has the probability of on is 1 and everything else is 0, right? If this generated, if this image actually generated this text, as opposed to that being the ground truth, but if it actually generated that, then what we know is the probability of on was higher than the probability of anything else. Okay. There are two ways you can use a generator to generate text. One way is just take the highest probability for each one. What's another way? Let's say instead of captions, this were something different, we'd fed in Shakespeare. And what it does is it spits out Shakespearean-like language, okay? So what we could do instead is do a random choice based on our probability distribution here, our softmax. So we could say with high probability we'll take the, but we might also take or some other words. And so we'd go through and we'd have a whole universe of possible captions. Okay? And we're just choosing one from that universe according to our probabilities. Did difference make sense? Okay. So let's look at the first word. And let's say we have a very small dictionary. So we have the, a, and umpire. And we say that that y hat at 1 equals, so the has probability 0.8, and a has probability 0.19, and umpire has probability 0.01. Our two choices are just take the maximum, or another choice would be roll the dice. 80% of the time we'll take the, 19% of the time we'll take a, and 1% of the time we'll take umpire. And then we do the same thing for the next, the next, the next, and so on.
Would that influence our choice like as we move along?
So yes, it would influence our choices as we move along. And there is a updated or a richer type of an RNN that actually feeds in to the state at any point in time, the old hidden state, the current input, and the output from the last time. Okay? So that'd sort of be important to have, because when the RNN is generating its fourth word, it probably wants to know exactly what the first three words we chose were. Okay? And so we would feed in our chosen word here, and our chosen word here, and so on. So we'd be feeding in a one-hot vector. We'd not be feeding in our distribution anymore, our softmax. Good question. Abba.
Would the only advantage of RNNs over CNNs be like when you have sequential things where you want each thing along the sequence to determine the outcome of something down the line?
Yes, you definitely, the RNNs, the difference is, so CNNs have spatial property. Regular old, fully connected or partially connected, could be whatever they are. And then RNNs have this idea of a sequence. Often we talk about it as time, but it's not really necessarily time. But it's just a sequence where the past affects the future. And so that we want to be keeping some state information.
So similar to how we have like the vanishing gradient problem in like CNNs, I can imagine how like you can have an RNN that like when you train it and you're trying to go back and like correct stuff, that it might not necessarily pay attention to events earlier in the sequence than like.
Beautiful question. We're going to talk about that on Monday. Yes, we can be going back in time a lot here, as we'll see in the backprop. And the fact that we go back and back and back and back and back and back means if we have either small gradients or big gradients, we can have this vanishing or exploding gradient problem. And so there's a couple ways to deal with that. But yeah, it may be something here really depends on something way back here. And so we need to be able to train for that.
In theory, like tacking on that question, a lot of these issues should be already solved, right, by these pre-trained networks and the way in which they do like regularization or other things that account for vanishing gradient problems.
Yes, they don't do normalization like that. Basically, there's designs. There's a careful initialization, and there is designs for more complicated cells here, more complicated states that give us a way to do longer-term memory and sort of get information back without having to go through those gradients. Okay. But we will get to that. Okay, mini to same. So we know we've got some state information. We know we shouldn't draw too many circles because it means a lot of other stuff you have to fill in. So we would have, how's the actually represented? Given that we're not actually feeding in the characters T and H and E. One uncoding, right. And so what would come out here then is a softmax, again, right? And we'd have the probability of article being high once it's trained, right? So we have basically the probability of article and adjective and noun and verb and preposition and whatever the other parts of speech are. Okay? So think of that as like a dictionary of parts of speech. And so our output is a softmax over that dictionary. So our third one, the probability of adjective is high. And in our last one, the probability of noun is high. Do we need a special end character or an end token? No, because we know how much we're feeding in and we know we're getting out exactly that. Questions on that? All right. Many to many. Many to many as opposed to, I think what I called it before is many to same. So many to same, one in, one out, one in, one out. Many to many, one in, who knows how much out. So we know what we're going to feed in is going to be English text. So we'll feed in the and quick, and we'll go all the way to back. Now we're doing language translation. What should be output once we've seen the word, we've seen the? It's not exact. We don't know what to put out yet. In fact, we're not going to put anything out for the because Russian doesn't even have articles. So yeah. So we don't know. And it may be that in the language we're going to, this is the word that comes first, right? If you do German, I've heard, or they do a bunch of nouns, and at the very end they kind of put 3 or 4 verbs, and you don't really know what's going on until you get to that very last word. And so it may be we've got to get to the last word before we even know how to spit out the first in their other language. So therefore, we can't do anything until we've seen everything. So we're going to keep going after we pass in back. In fact, we're going to make it a different color. So now we're going to say, we care about outputs now. So our output here is sort of either don't care or doesn't exist. Right? We're just not looking at it, so it might as well not even be there. Here, we're going to output the probability of bystraya is going to be high. Right? And we have another output here. And we have another output here. And here, the probability of sobaki is going to be high. Okay? So we've got all these words. Blah, 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 sobaki. And now we get the same problem we had before. How do we know when to stop? And so what do? Yeah, we have a special token that says end is high, right? Whatever we made up that token, and really it's just an entry in our dictionary. Make sense? How many dictionaries do we need? 2. 1 English, 1 Russian. Yep. Questions? Oh, let's say we're trying to do this translation. Is there any pre-training we could have done? Any transfer learning that we can take advantage of?
We could use the state output at the end of the English part and then not run all the way back through each time over the English part.
So we're using this, by the way, just to get back, this is an important point. So this arrow here is the only connection from the English to the Russian. So what is this? What does this represent? Say again? Our input in what format? This captures the meaning of the sentence. Right? It's got to get us from English to Russian, so it has to have everything it needs to get from English to Russian. This part, the green part, needs to know English. The blue part needs to know Russian. So it would be really good to pre-train this. Basically use a language model for English here, and use a language model for Russian here, and then smash the two together. It'll certainly be better than starting from scratch. Questions on this? Make sense? So we've done one to many to one, many to same, and many to many. But there's a few more interesting ones, like speech recognition, because speech recognition is kind of its own deal. So I am going to first do a simpler speech recognition, which is trigger detection. So you want to know when someone says Alexa, right? You're just feeding in audio into a neural network, and every once in a while it's going to pop and say, oh, someone just said Alexa. Okay? I better pay attention. So what do? First thing we do is feed this into, basically do a Fourier transform. And let's go back to the previous slide. Here's a Fourier transform, right, showing color. So we got our x-axis is time. Our y-axis is frequency. And the, let's say, sort of the z-axis is energy, I believe. So it tells us how much energy there is at each frequency at any point in time. So what we're going to do then is break this up. Into time steps. How big are these going to be? You know, not too big. Let's say 5 to 10 milliseconds. Okay? And so for each time step, we will to tell you the truth, I don't know whether we just sum up the frequencies across the 5 milliseconds or whether we provide, we sum them up. Okay? So we basically take all of this energy information from here to here and sum it up so that we have an overall energy for that period. Okay? So we might have, let's say, 50 frequencies that we're interested in. So we might have 50 frequencies and 5 to 10 milliseconds. So for each time period, we'd have 50 values representing the energy at each of the frequencies. Does that make sense? So we've got what do we call these? We'll call these, we'll call them samples. So sample 1, sample 2, all the way up to sample T. All right, and I'm making them tall and skinny to represent the fact that we're taking a slice of the spectrogram. These, of course, are going to be inputs to an RNN. And what do we want the output to be? Are we good with having just one output at the end? No, because here's our goal. Our goal is, where did they say Alexa? They finished saying Alexa, right? They started saying Alexa here, and they finished it here. So here's where they stopped. They finished with the word Alexa. Okay? That's what I want to know. And I want to know it immediately. I don't want to wait till the end and have you tell me, oh, it happened 2 seconds in or 15 seconds in, right? Because I'm listening real time and processing all this stuff and wanting to know, oh, they just said Alexa. So therefore, I need to have output all the time. And the output is basically, what's the probability they just finished saying Alexa? Does that make sense for each one of those? So basically, it's going to be a bunch of zeros and an occasional 1. Certainly, your ground truth is going to be a bunch of zeros and an occasional 1 right after the Alexa. Does that make sense? One problem with that is we've got an imbalance in zeros and 1s. We have lots and lots and lots of negative examples. Yep, no Alexa, no Alexa, no Alexa, no. Okay, here's one. It's very hard for it to learn from a small amount of positive examples because its loss function is going to tell it, you know, you're better off just pretty much say 0 because it happens so rarely. You're not going to get, if you just say 0 all the time, your loss won't be that bad, right? We can adjust the loss function to penalize not saying Alexa when they should more than the opposite. Alternatively, what we can do is we can say, you know what? Although this is where they finish saying Alexa here, let's just say for the next, I don't know, 10 time steps, let's just say, let's call those ones too. So they said Alexa not just immediately in the last 5 milliseconds, but over the last 50 milliseconds, right, which will be 10 of our time steps. So could be 10, could be 50, something like that. So we would expect to see zeros and then a string of ones. And that's what we'd be training it for. And that string of ones would make our training work better because we have a closer relationship with positive to negative values. That's all.
Well, we can also change the size of the discrete input that we take from the audio sample, right?
So how much, whether we're taking 5 milliseconds or 10 milliseconds?
Yeah, just like when we do the convolutions and we
Yeah.
take, let's say 3 by 3 and then take 5 by 5 and take just many so we can capture different sizes of
Yes.
input. We can also try to do the same thing.
Not very, here's the problem. As soon as they utter Alexa, we need to decide whether they said Alexa without waiting for anything in the future. So if we have a hierarchical, if I'm understanding your question right, in the CNN case, we had this hierarchy where we took 3 by 3s down to 5 by 5s, and we made smaller and smaller values. Part of what that also did is set up a hierarchy so that if we kind of look at the first pixel, in order to interpret it, you need to see other pixels as well. And here I'm afraid what's going to happen is, in order to interpret this time step, you need not only some stuff before, but some stuff afterwards too, if you're building stuff up in a hierarchy. So if it weren't for the real-time nature, that might work. Any other questions? Okay. I am going to just quickly talk about the speech recognition and say the output of the speech recognition is not something that looks like this. Okay? The output of the speech recognition is going to be more like phonemes that we may need to feed in to some further algorithm. So phonemes, anyone seen like in a dictionary where they show pronunciation and they show these funny letters like, what is it, schwa, and the International Phonetic Alphabet has things like theta, which is the th sound, and schwa is basically. And so we've got a bunch of others too. So it's more than just the characters in English, and it's all the sounds. So phonemes are sounds. And it's the building blocks of words. So in an international alphabet, this might be the, E, U, T. Of, I don't know what that would be, something A, they have some special ones for this, and like that, okay? So this is what we'd actually output. But we wouldn't just output this, because we'd actually want to do, like we did in the previous case, we want to have some output for every time step. So basically every time step would provide a softmax with a probability of what phoneme is being spoken, or nothing. Okay, so it's empty or phoneme. So what we might see if someone's talking slowly and says the, right? That was like, I don't know, 100 milliseconds of the, right? So we would have 20 time steps where we have probability of the being high. So we could have a bunch, so we have as many time steps as we have, that's many predictions we have. And so we'd have a bunch of duplicates. And we'd have to then go through and collapse duplicates and then run through some phoneme to word conversion, which would probably be a neural net.
For the phoneme to word conversion, basically, would we have two different truths
We would have a ground truth of sound to words. And then we could, for this training, it's easy to convert words back to phonemes, right? Assuming you know what, I guess you'd have to know, right, what accent someone has. Like British, you know, so the conversion to phonemes for British and US English is different. So that might be an issue. But you should be reasonably easy to go from words to phonemes. Okay? Because it's basically look it up in a dictionary. And even if you don't know exactly what it is, there are only a few choices. So. All right. Any questions? Backpropagation through time. So here's the deal. It's just a fancy way of saying regular backpropagation. Okay? If we've got a RNN here, time is moving up. In our previous examples we just showed, time was moving to the right. Okay. So time is moving up. All our errors are moving up and over and to the right. But as we go from state to state to state, we're clearly going up, 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 right? Forward in time. When we get to backpropagate, and we've got our y-hats here, and these y-hats all get combined into some loss function. Right? And now we want to backpropagate our error to our weights. Where are our weights? So few places. Every arrow would contain weights. How hard would it be to do the error here? Do we need any new machinery? No. We just take dl, dy hat 3, dy hat 3, dh3. That gives us our error there. So easy to compute. Easy. Easy. What about our red ones here from h to x? Well, actually, let me back up. Oh yeah, so we do want to adjust those weights because we're multiplying x times a weight and we want to be able to adjust that. So I claim this one is easy because computing the error to h3 is easy, and then from h3 to x3 is easy. Why is this one harder? Because we got two outputs, right? So when you have two outputs, the key is, so let's say we have our computation graph, and this is A, and B, and C, and D. If we want to know dA, dd, that's equal to basically the sum of the error via B and the sum of the error via C, right? So dA, dd would equal, and I should use partials here, but I'm not going to. Whoops. I knocked my video cord, and that turned out not to be a good thing. So 1 second. All right, we're back. So dAdd is equal to dAdB times dB dd plus dAdC times dCdd. Does that make sense? Because basically, there are two ways H2 can affect the loss, right, where this is taking the place of D. It can affect the loss this way through y hat 2, and it can affect the loss this way through y hat 3. And all we really need to do then is say, okay, in order to calculate the loss here, we just need to know the loss here and the loss here, and then we multiply derivatives, add them up. So what we're going to be doing is moving ourselves, right, backwards, which is where we get the name backpropagation. But the key is the down arrows are not just regular old backpropagation. They're actually backpropagation through time, because we're going down instead of up. Do you have to do something special if you're doing PyTorch with this? No. PyTorch says, oh, you did a bunch of computation. I'll do backward propagation for you to find gradients. Okay? Yeah.
Isn't the difference because the fact that the edges are not necessarily the difference, so they are different in the same set of weights?
So they are the same set of weights. It's no different from CNNs, where we're sharing weights for convolutions in different areas of the network, right, or different parts of the image. It's the same idea. So when we were looking here at the error, we're saying what happens if H2 increases by 1? Right? We basically want to say if H2 increases by some value, how much will the loss increase? And so the fact that this is using this weight function, or let's say even here, where we're reusing the same weight, doesn't really matter. Because we've already taken the fact that this is duplicated, we've already sort of taken into account. It'll maybe make more sense when we look at the equations. But the short answer is no. It doesn't really matter that they're duplicated.
These are three different weights, right? The red,
These are three different weights. The weights that take us from X land to H land, the weights that take us from H to H, and the weights that take us from H to Y. Three different sets. Yeah. And we could theoretically have more between here and here if we wanted. We could have a little network here like we did with our CNN, or we could have a little network here like we did for one of our examples where we're looking at sentiment.
Are we saying that all the red ones, all the yellow ones, and all the blue ones are always the same?
All the red ones, all the yellow ones, and all the cyan are all the same.
But would there ever not be a time like when if you had a sequence of inputs, would you ever not want to weigh some subsequence more than the others? Like something along the lines of like, I care more about what happens from the fourth going to the fifth as opposed to like the first.
So it's unlikely. The question is, can you change so you have more emphasis on stuff at different parts of the sequence? So it's more likely, rather than saying from the fourth to the fifth, if you've got some situation where sort of which element in the sequence matters, it could still count, right? It could be possible for it to count in one of its hidden states and do that. But it's more likely, like after you see the word the, look for the word something else. And so when it sees the word the, it can be setting some state information in here that it then uses at the next step in reading in the X.
When you say like this one, like the first down arrow is still pretty easy, right? Because like it's only the second arrow that should be hard.
Okay, I'll even agree with that. Yeah, the first.
Finding gradients with respect to like H, not the weights, right? And it's like finding the gradients with respect to
Yeah,
H.
that one's easy. And I guess actually once we start saying this one is easy, then this one becomes easy. And so therefore it becomes meaningless. So this was less easy just because we had to combine. And I guess if we're combining and calling that not easy, then we should say this one's not easy either. Does that make sense? I mean, I will rephrase this right now, and I will say, we're going to call this what step could you do this in? Okay, so we could do this in step 1. We could do this in step 2, and this in step 2. We could do this in 3, and this in 3, and this in 4, and this in 4. That might make more sense as opposed to just talking about easy. The formula. So this is the formula from yesterday, where we have our recurrence relation for h at t, and we have our base case. And then we're saying y hat is just equal, I mean, no big deal here. And then we also have our loss, and this is important to look at. So we have our loss for a given output, right, at a particular time step. So this is at time step t. And this could be any loss function you want. I just happen to be showing the cross entropy loss here, right? So I'll just say here, it could be different, depending on what you need. This is common, that what you care about in terms of y and y hat, right? Where y hat really is y hat over a sequence, the entire 1 to capital T, that it's just going to be the sum of the individual losses. Now, in some cases, that's not true. When we were looking at the sentiment analysis for IMDb, which y hat do we care about? The last one. And so we'd say the total loss is just equal to the loss of the last one. And by doing that, we're ignoring the rest of the y hats. We never look at them. They'd never be used for updating any weights. Yeah? Okay.
So just curious, so in what instances would all of them be of importance to us?
A good example would be when we were looking at the parts of speech for an input. And there, we care, is the correctly say preposition? Does dog correctly say that it's a noun? And we just want them all to be right. None of them count any more than any others. You could imagine a loss function as well that somehow doesn't want them equally weighted and doesn't care about a single one, but maybe cares about some parts more than others. Okay. So let's look now at back propagation through time. So we've got the derivative of the loss with respect to the last layer. So the last, this is our state, our hidden layer. Well, that we said is pretty easy. We just need to know what the loss is to y hat, the last y hat, times the derivative from the y hat to the h. Straightforward? Okay, now let's look one back. So time step t minus 1. So the next to last. Well, here, there are two inputs, right? We've got our, well, there are two outputs, which are our y output and our h super t output. So therefore, we've got two ways in which we're getting a gradient, from above us and from our y hat. So the y hat part is here. So this is from the right. And this is just basically the same as the one above. And this is from above. And we only we don't have that one at the last layer because there is no above at the last time step. I shouldn't say layer. Yeah.
From right from the loss?
It's from, yeah, it's from y hat at t minus 1, which itself is then from the loss. Right?
The first equation is just for the last layer, for the top rightmost h.
The topmost h. Yeah, that's for this h. And then t minus 1 is this one, and then t minus 2 is going to be this one.
Oh, so the vertical is time and the horizontal.
Yeah, so this is time. The horizontal is x goes to h goes to y.
And we're still calling that layers.
Yes, we would call that layers. Yes. So, and in fact here I'm saying layer, and forget that, time step, next to last, time step. Okay? As we go on to the next one, right, t minus 2, we've still got our contribution from y hat, which looks just like the rest of them. And then here, we've got the loss to ht, the loss from ht to ht minus 1, the loss of ht minus 1 to t minus 2. So as we go down to earlier time steps, we're going to have a larger and larger set of these partial derivatives to multiply together. And they're all going to be very similar, right? It's going to be from h at some time step to an h at some previous time step. Yes, previous time step.
For the last later half, from above.
Yes.
That was the x and the h, right? That was considering like from the x and the h.
No, not from the x and h. It's from the y and the h. Right? So basically we have our h here, h at t minus 1, and we've got a contribution. We've got an outgoing arrow to h at t and an outgoing arrow to y hat at t minus 1. So when we're doing backward propagation, right, we also have an incoming arrow from x, but we don't care about that because when you do back propagation, it doesn't affect it, right? Questions? Okay, so we can write a more general case that the derivative of the loss with respect to h at t minus I is, well, the derivative of the loss with respect to that guy's output times the derivative from that output to this, plus the product of a bunch of derivatives. Well, we've got first the derivative from L to the topmost h, and then we've got from that h to the next h to the h after that, the next h to the h after that, and so on. Does that make sense? And we're familiar with the pi, right, the multiplication instead of sigma for addition. So yes, sigma is sum, pi is product. Okay. Does that one make sense? All right, I wanted to look in more detail at the computation of the loss to a particular hidden layer. All right. So we know that the loss to a particular hidden layer, right, so we've got a layer here, and that I am saying layer, and I mean time step. Okay, so time step. So we've got here a time step, t minus 1. And I'm going to show the hidden state. I'm going to kind of zoom in on that. Any guesses what those represent? These are the 6 pieces of state that we actually store here. Right? We store 6 numbers. We've got 6 activations coming out, or a vector of 6 coming out. Right? So it's 6 neurons inside our state. And if we go up to the previous state, well, I guess it's the next state, so it's time step t. How many of those red circles do we have? We better have 6, because we have the same amount of state. Right? And connecting these is a weight matrix. What's the name of that weight matrix? It's W for weight, HH, because it's from H to H. So that's a fully connected layer, right? Or I guess it's really a fully connected connection. I shouldn't say layer. Does that make sense? So we get to decide how big we want this state to be. How much do you want to store? For bigger problems, we need larger amounts there. Okay, so here's what I'm looking at. I'm going to erase these lines here and put them in one by one in a moment. What I'm saying is, this is not just the loss to h at t minus 1 as a whole. because we've got this I here. So we want to know this guy, the ith neuron in the state. We're looking at what's its loss. Okay? That is, if we just poke this one up a little bit, how much is that going to change the loss? So how do we do that? Well, how many outputs does this guy have? He's got at least 6, right? We've got one going to here and one going to every one of the other neurons above us. Let's just focus on that right now because it also goes somewhere else. Where else does it go? To the right. Exactly. It goes to the y hat as well. So we know it has 6. I'm going to look at one of them. Let's look at this one. So we're going to 2 here. So we're at I here, and that's going to be actually J up here. So what we say then is the loss is the sum of every one of the losses to the neurons in the time step above us. Does that make sense? So we're going to go ahead and say, okay, what's the loss from J? The loss from L to I is the loss from L to J and from J to I, and we sum that across all the J's. So that's what we've got here. This is all of the neurons in hidden state at time step t, which is exactly what it says, right? dl dh super t sub j times the derivative of h super t sub j to the derivative dhi t minus 1. Okay? So this is all the up connections from a single neuron. And this is all of the right connections from a single neuron. Because, right, we have over here y hat, t minus 1, and it has in it maybe a bunch of neurons. What's the most we've seen so far? When we're doing text and it's trying to generate text, it could easily be a 50,000 word dictionary, right? So we could have 50,000 neurons in there. So we can then also look at right, this goes out to every one of these neurons here. And so we can similarly then sum over those. The difference with what we've seen before is before we were seeing vectors, and now we're seeing single numeric values. Yeah?
It's maybe a silly question, but the 6 small kind of neurons inside of
Yep.
this, how do we determine that? Is that like
We say how big a hidden state do we want? 6, 50, 100.
similar to how we've done earlier, like we specify the number?
Like we specified 3 by 3 convolutions. Same idea. It's just something you specify when you create it. And it's a hyperparameter.
That J should be a bit different. Both J's, right?
That's okay. It's separate summations. I can reuse the same. Right? It is, well, we'll just keep in mind, we'd have a problem if they weren't parentheses like that. But if they're parentheses like that, there's no problem having a J, because it's only bound for the scope of the summation. But if it's confusing, I'm sorry. Okay, so does that one make sense? Any questions on that?
Just to be clear, but
Yep.
when we have the lines connecting like the different H's and the X to the H, we say that the weight, the two like the lines that connected them, they signify the weight.
The lines signify like a matrix multiply. So the weights are sitting there, yeah.
But the biases still exist. We're just like pretending that's like the weights and the biases, right?
Oh, there's a bias too. Yeah, I'm just ignoring the bias, but yeah, there's a bias too. So we're going to now go on saying we'll just keep the loss to that particular neuron above as a partial derivative. And we're going to say, what's the derivative from here to here? That is, what's this derivative? Right? From j above to I here. Well, we know how it's calculated, right? We know that hj at t equals what? We've got some calculation. It's g sub h of, and we're multiplying together some matrices and weights. As far as this guy's concerned, we've got two summations, right? Plus a bias. So we've got the summation for some w's times h t minus 1. And then we do the same thing for x. Okay? We can ignore x, right? Because that's just a constant. So when we take the derivative, that's going to go away. The bias is going to go away. We're left with what's here. So basically, we're going to have the summation of a bunch of weights times particular h's. Well, for all but one of these, it's a constant, right? Because we're going to be caring about the derivative with respect to the ith one of these. So the ith one of these is going to still be here, and all the rest of them are just going to be constants that when we take the derivative will go away. Does that make sense? So what are we left with? If we want to take the derivative of this with respect to this, chain rule, so we're going to have g prime sub h of, let's h of t, hold on a second. No. So I was trying to be so careful on my slides. G prime h of the equivalent of z, right? The weighted sum. Whatever's in these parentheses, the weighted sum, is what we're taking g prime of. So we're going to just make a quick update there. Times what? Times the appropriate weight. Well, what's the weight that takes us from I to j? It's W ij. Which W matrix? The HH matrix. So it's the ith row, jth column of the WHH matrix. So that is the derivative from that one neuron above to our neuron here. And then we would multiply that by the derivative from the loss to that neuron above. And we do the same thing for the y's. Well, if we want to look at, now we don't have the I subscript here. So we're looking at the entire vector. So it's just going to be a vector of the derivative to the first neuron, to the second neuron, all the way down to the last neuron in the hidden layer, right? So it's just basically a bunch of these in here and in here and so on. We know what every value in here should be from this. And what we can show is that it's the same thing as taking so let's look at this, let's break it apart. This dot product G prime H of Z, that's just this part, right? It's just this part that's multiplied by each one of these. So we can go ahead and, assuming we've calculated the vector, then just do a dot product and multiply it by our G prime. So that takes care of the G prime. Now we've got the summation, the derivative L with respect to the particular neuron. So we can break that out into a larger vector. And then when we do our weight multiplications here, we will end up with let's see. So the loss, this is going to look like, that's this one. And this one is going to be transposed W. HH. And so as we go through and do each of those multiplications, it's exactly this summation here. So we're going to want W 1, 1, 1, 2, 1, 3, 1, 4. Okay? Because if we look at what's varying here, it's our J that's varying. So we want W11, W12, W13, and so on. And unfortunately, we're just ending our time. But if we're just almost done to basically show that these are the values we want in our matrices. And then we do the same thing for the y's and add them together. No different from any other backpropagation. We just have a fancy name for it. Any questions? All right, so come Monday, we'll talk a little bit more about backpropagation. We'll then talk about bidirectional recurrent neural networks. We'll talk about the vanishing and exploding gradients, how we deal with that. Okay? Have a good weekend. And your assignment is due Tuesday night instead of Sunday night. Our office hour, I'll be there all afternoon today. Mm-hmm.